In this segment, we're going to find out what the transverse tensile strength is of a unidirectional lamina. We'll be first modeling the problem, and then we will take an example. And after that, we will also look at how do we find this transverse tensile strength experimentally. So this is a representative volume element to calculate the transverse tensile stress. So what we are doing is we're applying some load, some stress sigma 2 in the direction perpendicular to the fibers, and we want to find out what is the ultimate stress which you can apply in that particular direction. So if you look at the representative volume element, will look like this. So this is given by the dotted red line here. And so what is D? D is the diameter of the fiber. And what is S? S is the spacing between centers of fibers. Okay, the joining ones or the closest ones. So that becomes the representative volume element, and we're going to use this representative volume element based on this stress being applied in direction perpendicular to the fibers to be able to figure out how we can model the problem. So if we look at this again, let's concentrate just on direction 2. So let's just concentrate on direction 2. And what we're going to do is we're going to only look at the normal stresses and normal displacements and normal strains in direction 2. That's what we're going to do. So what we'll have is that the displacement in the composite will be same as the displacement in the fiber plus the displacement in the matrix. Makes sense, because how much the fiber moves and how much the matrix moves will be the total displacement in the composite itself. Now, using the definition of strain in the composite, because S is the width on which width of the composite in this representative volume element, so that gives us a displacement in the composite. Displacement in the fiber will be given by this in terms of the strain in the fiber, and the displacement in the matrix will be given by this this strain in the matrix itself. S minus D is the amount of width which is taken by the matrix. As you can see, that this distance here is S minus D. So simplifying it, we get something like this. Now, if you look at, you draw a cross section here, and you draw a cross section here in the fiber itself, you'll find out that the force which the matrix will be experiencing, the normal force in the direction 2, will be same as the normal force experienced by the fiber. And since the area on which these forces are acting in the fiber and the matrix are the same, that means that the stress in the fiber is same as the stress in the matrix. This is all in direction 2. So that means that EF times epsilon F should be equal to EM times epsilon M. And that gives me this as my strain in the fiber in terms of the strain in the matrix. So the only reason why we're doing this is because we want to write this whole thing just in terms of the strain in the matrix. So we get epsilon C is D by S, EM by EF, epsilon M plus 1 minus D by S epsilon M. So now what we can do is we can say that, hey, what is the ultimate strength in direction 2 will be based on, hey, how much is the strain, ultimate strain in direction 2, and that will tell us, hey, what will be the ultimate strength in direction 2. So let's go ahead and do that in the next slide. So simplifying, we get epsilon C is D by S, this particular expression right here, times epsilon M. So if I want to find out, hey, what is the ultimate strain which I can apply in direction 2, that means that I have to take the ultimate strain which the matrix can take in tension in direction 2. And since I know that the strain in direction 2 will be given by the stress in direction 2 divided by the Young's modulus E2. I will get this. Hence, sigma 2t ultimate will be equal to this as our final expression to find the ultimate tensile strength in direction 2. So let's go and see that how we can use this to solve an example and find out what we are predicting as our ultimate tensile strength in direction 2. So this is the example which we want to do. We want to find out the ultimate transverse tensile stress which we can apply, or the transverse tensile strength. We have 60% fiber volume fraction of a glass epoxy lamina. We're given that the fibers are circular and in square array. The Young's modulus and the fiber in the matrix are given. The Poisson's ratio of the fiber in the matrix are given. The ultimate strength of the fiber in the matrix is given. And we want to find out the ultimate tensile strength of the unidirectional lamina. So all we have to do is to apply the formula which we just derived and be able to do so. So the formula which we have is, let's write it again so that we know what we need to calculate. So it's given by this formula here. Since that's the case, we have to find E2. We have to find this ratio of the diameter of the fiber to the spacing between the fibers. And we have to find the epsilon mt ultimate, which is the ultimate tensile strain which the matrix can take. So let's do that one by one. So we're going to use the reciprocal formula for Young's modulus in direction 2, which is given by this formula right here. The volume fraction is 0.6. The fiber Young's modulus is 85 gigapascals. The volume fraction of the matrix will be 1 minus 0.6, which is 0.4. And the Young's modulus of the matrix is given as 3 gigapascals, and that gives us 7.123 times 10 to the power 9 as the value of E2 pascals. Let's look at the other variables which we have to calculate, which is d by s and epsilon mt ultimate. So the d by s ratio is given as by this formula for a square packing array and the fibers being circular. So that gives us 4 times 0.6 divided by pi, square root of that, which is 0.8740. Now let's go and look at what the epsilon mt ultimate is, which is the ultimate tensile stress which the matrix can take. So we know that the ultimate strength of the matrix is 70 megapascals. The Young's modulus is of the matrix is 3 gigapascals, and this gives us 0.0233. This formula is basically coming from sigma m ultimate divided by the Young's modulus of the matrix. If you wonder where we got that from. So once we have that, let's go and find out sigma 2t ultimate from our formula. So it is equal to E2, which is we found as 7.123 gigapascals. Now d by s, which is this, em by ef, 3 gigapascals over 85 gigapascals, then plus 1 minus d by s, and this whole thing is multiplied by epsilon mt ultimate, which we just calculated, which is this number right here. And once we do that, we get this as our value for the sigma mt ultimate, and which we can write as, hey, this is same as 26.06 megapascals. So the next thing is that how do we find out the ultimate tensile strength in the direction 2, or the transverse tensile strength experimentally? So the thing is, if you remember your longitudinal tensile strength, we use ASTM D3039 standard. We're going to use exactly the same standard here as well. The only difference will be that we'll have the coupon with 90-degree plies. So we'll have 90-degree plies because, of course, we are finding the transverse tensile strength. So because the 90-degree plies will fail at a lower load, if we use the same number of plies, like we use 6 to 8 plies in the longitudinal experiment, we use 16 plies instead. So that way the load at which it will fail will be a little bit higher than if we only use 6 to 8 plies, as in the longitudinal tensile strength test. So far as the strain gauge is concerned, we only need the strain gauge in direction perpendicular to the fibers right here, and that'll be this direction. And this will allow us to find what the Young's modulus in direction 2 is, or E2. But you can always put the strain gauge in this direction as well. That is parallel to the fibers. So this is epsilon 2, this is epsilon 1. The reason why you might want to do that is because although this is going to give you Young's modulus in direction 2, along with the stress which is being applied in direction 2, but minus epsilon 1 divided by epsilon 2 will give you the minor Poisson's ratio, nu to 1. So if you find nu to 1, then we also know that, hey, there's a reciprocal relationship which is given by this. So since we have a reciprocal relationship, we can always check that whether that reciprocal relationship is turning out to be correct or not, or how accurate that reciprocal relationship is being duplicated by our experimental results. These are some typical results which you get. As you can see here is that we are using 16 plies rather than 8 as we use for the 0-degree ply or for the longitudinal tensile strength experiment. And all you're doing is simply the same thing. We are going to plot the transverse tensile stress as a function of transverse tensile strain. Take the slope of that. That'll give us the Young's modulus in direction 2. This is the ultimate tensile strength in direction 2, and this is the ultimate strain in direction 2 right here. And that's the end of this segment.